Welcome back for the fifth installment of the AP ECE Chemistry Chapter 13 Acids and Base problem set. Let's take a look at problem number 75. In problem 75, you're told that you're dealing with ammonia NH3 and a pH of 11.68. You're asked to find how many grams of NH3 are actually needed to be dissolved in a 1.25 liter solution to get that pH of 11.68. So I kind of lay out a program down here, 1 through 6 of your steps to follow, and then sort of your work's over off on the right side. So obviously write an equation to start. So here's our equation, NH3 plus H2O gives you NH4 plus OH. And after this would be a K. That's right, B. Right here, there'd be a KB present there, because it's a base type equation. Then you set up an ice table, but an abridged version. But you need to do a little calculation to kind of figure out what should go in your ice table. And that's what comes in as 3 and 4. Part 3, since you're only told what the pH is, you can figure out what the H plus ion concentration is as described in previous screencasts for this problem set. You find the H plus ion concentration is 2.0 times 10 to the negative 12 molar, and then since the Kw is equal to H plus times OH, and that's 1.0 times 10 to the negative 14th at 25 degrees Celsius, you can find the OH concentration as 4.79 times 10 to the negative 3rd molar. So then that should be what your concentrations of NH4 plus and OH minus are at equilibrium if the pH really is in fact 11.68. So first you write your equation, then you set up your ice table, then you start to populate your ice table with 3 and 4. Write your Kb expression. Kb is equal to 1.8 times 10 to the negative 5th. That's a book value for the Kb associated with NH3. And then you have your products, NH4 plus and OH minus, divided by your reactants, and NH3 plus, ignore your water. You plug in your values, you know what the two values for the NH4 and the OH are, and so that's 4.79 times 10 to the negative 3rd. That's the concentration of OH that you found in part 4. And you square that, divide that by the concentration of NH3. You can find out what the concentration of NH3 is because you know what Kb is mathematically 1.8 times 10 to the negative 5th. So when you solve out for NH3, you get 1.27 molar. So then you calculate your mass from the molarity, 1.27 molar, and then you convert your moles into grams with the molar mass, and then you convert into, based on the liters, to cancel out your liters, you need 27 grams of the ammonia to make a solution that is 11.68 in pH. Let's take a look at problem numbers 79 and 81. These are actually going to be like a tandem set of problems. These will put together, they kind of fit together nicely. In 79 and 81, you're asked to find out, are these solutions acidic, basic, or neutral? And then you're supposed to talk about why and justify why they're acidic, basic, or neutral. So there's a few questions you need to ask yourself when you're looking at a particular ionic compound formula, like K2CO3, when trying to decide if, when put into water, if it will make an acidic, basic, or neutral solution. So the first question you want to ask yourself is the cation from a strong or weak base? If the cation is part of a strong base, you get to ignore it. Second question you want to ask yourself is the anion part of a strong or weak acid? Because if the anion, the second part of the ionic compound, is from a strong acid, then you get to ignore it as well. And then if it gets a little sticky and you can't kind of decide, you might want to write further equations and compare your Ka and Kb values. Those are your basic tips for this one. So let's take a look at part A. You have K2CO3. K plus, there would be two of them technically from each formula unit of K2CO3 that dissolved. The K plus comes from KOH, a strong base, and you get to ignore it. CO3, however, comes from a weak acid, so you write an equation to kind of describe how it would work, and CO3 2- has a negative charge and can act as a base and accept an H plus from water to make HCO3- aqueous, and then also some OH. So in this case, part A, K2CO3 would be a basic substance. For part B, you have NH4F. So NH4 is a weak acid, F- is also a weak acid. You have these two weak acids, and with their weak acids and their, quick correction, NH4 plus is a weak acid, and F- is from a weak acid, so F- will act like a base, which is why there's a Kb value here. So you have to compare the Ka and Kb. The Ka is greater than Kb, so therefore this will be acidic. Part C, LiH2PO4. The Li is from a strong base. You get to ignore it. The H2PO4 can actually kind of do both things. It could act as an acid or a base, and here's an equation for it's acting like an acid. You can see a Ka associated with it, and here's an equation for acting like a base. Take a look at those and see if you can identify why they're actually acting like an acid or a base. But the Ka is greater than the Kb, so this one will be acidic. Part D, the Na gets ignored. The NO3 is from a weak acid, so it's going to act like a base, so this one should be basic. Part E, you're going to get a neutral thing. Both Ba and ClO4 come from strong things.